a function phi from G to G bar is called an isomorphism if what? Three conditions have to hold. I'll write them as a list of three conditions. One, phi is 1-to-1. I'll write that as 1-1. Two, phi is onto. And three, phi is operation preserving. A new concept here. Operation preserving. OP. But what does that mean? Meaning, and if I put this definition on the test, you should say what that means, like I'm saying right now. It means if you plug in A times B into phi, that's equal to the product of phi of A and phi of B. Phi of A times B equals phi of A times phi of B. That's what it means to be operation preserving. Since we're low on time today, maybe the best thing to do with the few minutes we have is just illustrate that you've seen this concept before. I mean, I've mentioned it before. I've mentioned isomorphism before, but you've actually seen it before in another context, a couple different contexts. You might have talked about graph isomorphisms in discrete math, but a little bit more related is the concept of an isomorphism in linear algebra. That'll be a linear algebra example to end class today. Let G and G bar be the same group, which is, let's say, the plane R2. In linear algebra, you could say what I just said. You could call R2 the plane, two-dimensional space if you wanted to. Although in linear algebra, you don't typically think of the elements of this as being elements of the set as being points in the plane, but instead vectors in the plane, which you typically write as column vectors, like this. Column vectors with components or coordinates x and y that are real numbers. This is a group under what operation? Not vector multiplication. We don't multiply vectors. I mean, you can find the dot product of vectors and maybe the cross product of three-dimensional vectors, but that's not a group operation. Neither of those is a group operation. The dot product of two vectors is a number, not a vector. So closure is not satisfied. It's a way to combine two vectors to get something else, a number in that case, but it's not another vector. It's not an element of R2. So the operation is not any kind of multiplication. It's vector addition. I could call it ordinary vector addition if I wanted to. Any linear transformation from R2 to itself that's also 1-to-1 and onto is an isomorphism, a group isomorphism. Any linear transformation, as you learned about linear algebra, T from G to G bar, which in this case means from R2 to itself, that is 1-to-1 and onto, is an isomorphism. A group isomorphism. It also turns out to be a vector space isomorphism, as you learn in linear algebra, which implies a little bit more than being a group isomorphism. Any vector space is a group under addition, but with vector spaces, you also have scalar multiplication involved, which we don't with groups. As an example of such a transformation, so this is like a sub-example, if T of xy is defined using a matrix A times xy, where A is an invertible 2x2 matrix, that's one example. Oh, 1, 2, 3, 4, for example. Which, if you go ahead and multiply it out, the formula can be written this way. That's one example of a group isomorphism. Why? Why? Because in linear algebra, you learned that to be a linear transformation means to be operation preserving. It was written like this in linear algebra, I believe. T of u plus v, vector u plus vector v, is T of u plus T of v. And that happens with this matrix multiplication, that property will be true, essentially because of the distributive property of a matrix times the sum of two vectors. And this property right there, that's operation preserving. It matches this property, just different notation. Instead of a phi, we have a t. The function name is t instead of phi. And instead of group multiplication, abstract group multiplication, we have vector addition. But vector addition is the group operation in this group. So these two properties really are the exact same thing with just different notation.